In this example problem, we'll use a straight line graph of concentration and time to determine our integrated rate law, differential rate law, and the half-life for second-order reaction. Our problem reads, data from the reaction BC produces products is plotted below. In part A, calculate the concentration of BC at 60 seconds. For part B, calculate the rate of reaction at 60 seconds. For part C, calculate the first half-life for the reaction. And for part D, calculate the time it will take for the reaction to reach 95% completion. First, we'll calculate our concentration of BC at 60 seconds. Our graph is 1 divided by the concentration of BC versus time for a straight line. This means the reaction is second order with respect to BC. Our integrated rate law is then 1 divided by our concentration at time t for BC equals our rate constant K times time plus 1 divided by our initial concentration of BC. From the graph, we know that our rate constant K is equal to the slope, which is rise over run, or 5 subtract 2 divided by 30 seconds, and it's equal to 0.1. To find 1 divided by our initial concentration, it's equal to the y-intercept, which is just 2. Plugging these into our integrated rate law, and solving for t equals 60 seconds, we get 0.1, our rate constant, times 60 seconds, plus 2, which is our y-intercept, and that equals 8. So 8 equals 1 divided by our concentration of BC at 60 seconds. So for our concentration of BC at 60 seconds, we have to take 1 divided by 8, which is 0.125. Next, we'll calculate the rate of reaction at 60 seconds. This reaction is second order with respect to BC concentration, so our rate is equal to the rate constant times the concentration of BC squared. We've already calculated our concentration of BC at 60 seconds. It's 0.125 molar. And we found the rate constant K was 0.1 based on the slope. So plugging these in to our differential rate law, we get rate equals 0.1 times 0.125 squared, or 1.6 times 10 to the negative third molar per second. For part C, we calculate the first half-life for the reaction. Since this is second order, our half-life equation is T1/2 equals 1 divided by our rate constant times 1 divided by our initial concentration. Our rate constant is 0.1, which is based on the slope, and 1 divided by our initial concentration is our y-intercept, which is 2. So for T1/2, it's 1 divided by K, or 0.1, times 2, or 20 seconds. And in part D, we calculate the time it takes for the reaction to reach 95% completion. We can use our integrated rate law. 1 divided by our concentration at time t equals our rate constant, 0.1, times time, plus 1 divided by our initial concentration, which is 2. For the reaction to be 95% complete, we have to have 0.05, or 5%, of our initial concentration remaining. So to calculate our initial concentration of BC, we know that our y-intercept is 1 divided by our initial concentration, which is equal to 2. So if we invert this, we'll get 0.5 molar, which is our initial concentration of BC. So we want to solve our integrated rate law for when our concentration is only 5% of our initial concentration, or 0.025 molar. Plugging in 0.025 molar into our integrated rate law for our concentration of BC at time t, we can solve for time. We'll subtract 2 from both sides and divide by 0.1, and completing this calculation, we'll get 380 seconds. So at 380 seconds, our reaction should be 95% complete.